Latitude Media, covering the new frontiers of the energy transition.
I'm Shayle Kann, and this is Catalyst.
There's a lot more uncertainty on the demand side of the equation, largely coming from how much energy data centers are going to be consuming. That's where you may even get order of magnitude levels of uncertainty in terms of future power demand.
We definitely have order of magnitude level uncertainty in future power demand, like even just the forecast. Take all the different prognosticators on how much load growth there's going to be in 2035, and there are huge margins between those forecasts because nobody actually knows. Coming up, 5 intriguing questions about the future of electricity with Andy Lubershane.
The AI boom is here, but the grid wasn't built for it. Bloom Energy is helping the AI industry take charge. Bloom Energy delivers affordable, always-on, ultra-reliable on-site power. That's why chip makers, hyperscalers, and data center leaders are already using Bloom to power their operations with electricity that scales from megawatts to gigawatts. This isn't yesterday's fuel cell. This is on-site power built to deliver at AI speed. To learn more about how fuel cells are powering the AI era, visit bloomenergy.com or click the link in the show notes.
Surging electricity demand is testing the limits of the grid, but Energy Hub is helping utilities stay ahead. Energy Hub's platform transforms millions of connected devices, like thermostats, EVs, batteries, and more, into flexible energy resources. That means more reliability, lower costs, and cleaner power without new infrastructure. Energy Hub partners with over 120 utilities nationwide to build virtual power plants that scale. Learn how the industry's leading flexibility provider is shaping the future of the grid. Visit energyhub.com.
I'm Shayle Kann. I lead the early stage venture strategy at Energy Impact Partners. Welcome. All right, this one is fun. Andy Lubershane, my partner at EIP, our head of research, who you know and love if you listen to this podcast, is back. And this time he and I just came up with a list of what we think are 5 interesting questions that we're both thinking about, largely as they pertain to the world of AI, power, load growth, and all the technologies that are benefiting from that. So we have some general questions about what's going to happen in this market, and then some specific questions about technologies that may be benefiting from it, but still need to prove themselves out at scale. I won't belabor it too much. Here's Andy. Andy, hello.
Shayle, I'm back.
You're back. All right, we're just going to do a bunch of interesting questions that you and I have been going back and forth about, all under the umbrella of the thing we keep talking about, the thing everybody's talking about in energy world, which is the load growth in the electricity sector driven predominantly by AI. So we're going to talk about some of that specifically, and then some of the, I guess, reverberating effects that we've seen on technologies. I think we'll start a little broad, and then we'll get more specific and talk about a few technologies specifically. But let's start with a broad one.
It's the theme of the decade.
It is the theme of the decade. It's certainly the theme of this decade so far. Well, actually, the first question is maybe it stems from that, which is sort of a question of, will it be the theme of the next decade or the end of this decade? So here's the question, right? I think undeniably, we are currently in a state of undersupply. If the supply-demand balance between available electricity capacity at large scale, at least, and supply is mismatched. And that's why we have these interconnection queues, and that's why we have the long wait times, and that's why gas turbines are sold out, and all this kind of stuff that we talked about. And that is definitely the state of affairs today. I don't think anybody's going to debate that. Here's the interesting question. When could supply-demand mismatch flip back the other way? And if it happened, what would cause it? In other words, when could we enter a state where, oh, wait a second, there was a lot of overbuild, and suddenly there are a bunch of empty shells of data centers or electricity load growth underperforms relative to expectations, et cetera. Do you have a view on when that might happen and why?
It is so difficult for me to try to answer this question. It's very difficult to imagine that balance flipping the other way. it's possible for me to imagine the supply-demand mismatch becoming alleviated over the next 5 years, or that, the supply does not grow as much as we currently anticipate. And so demand is able to keep up better than we've been expecting in the next 5 years. For it to flip back the other way is practically impossible. I feel like my past, 18 months, every conversation I've had has been talking about all the reasons why we are in the scenario we're in, which is that supply is falling short of demand by such a wide margin, or appears to be falling short of demand by such a wide margin. But stretching my imagination, I guess there's two ways that could happen. It's two ways that we could alleviate this imbalance and maybe flip back. One would be that on the demand side, we're very wrong, or the variables causing demand to grow so rapidly change substantially. And the other would be that the variables on the supply side change substantially. I think demand is more likely because there's a lot more uncertainty on the demand side of the equation. And that uncertainty is largely coming from how much energy data centers are going to be consuming. And there's like multiple reasons for that uncertainty, but I think that's where you may even get order of magnitude levels of uncertainty in terms of future power demand.
We definitely have order of magnitude level uncertainty in future power demand. Like even just the forecasts, take all the different prognosticators on how much load growth there's going to be, how much power demand from AI there's going to be in 2035. And there are huge margins between those forecasts because nobody actually knows. And like you said, there's a bunch of different dynamics that could drive it in one direction or another. There's actually one that I think is interesting, sort of question mark on future demand. David Kahn from Sequoia, who's a friend of mine, has been putting out this kind of like series of posts. He started with the $600 billion question maybe a year ago, which was like, at that point, $600 billion in CapEx announcements had been made in data centers. And he's like, that has to pay itself back somehow through actual demand in the economy for the services from that AI. And that's the number, that's the bogey that they have to hit. And now the number is who knows how much more. And he's been doing a series since then that's sort of looking at like where's all the money for the CapEx coming from, who's actually paying for it and taking the demand risk. And it's definitely there's definitely some risk that there is more investment being made into data centers than there is real economic demand for those services. But it's not clear to me how long it would take for that to trickle through to, oh, wait, load growth isn't going to be as large. Like part of this is I think that the inertia on both sides of this it's the opposite of inertia. The momentum on both sides of this is going to mean that like if the train stops, it's going to take a while to stop.
I think that's right. I wrote a post on Steel for Fuel about this a little while ago called, why does nobody know how much energy AI will consume? And I think that's one of the big variables that you just pointed out, which is just the demand for AI is still uncertain. There's a big error bar in terms of how much individuals and corporations are going to be consuming AI, which is related to, how much better are these models going to get? How quickly are enterprises going to figure out how to apply them in their businesses? As well as you pointed out, just the profitability of the industry. And I do feel like that is a variable that currently feels like it has a tremendous amount of momentum. Feels like, almost nothing could stop the train of investment of tens of billions of dollars, hundreds of billions of investment that's going into AI research and AI data center construction right now. But there are a trickle of stories now in mainstream press and in business press, the Wall Street Journal, et cetera, that mention the word bubble, right? And it isn't entirely clear how sustainable this level of investment is. And economic bubbles are the sorts of things that can pop quickly and surprisingly. They have in the past. And so I'm not taking a position right now personally on how bubbly the behavior is out there in the market, but that is clearly a risk. That's one vector of risk in energy demand growth world, is that something causes investors to fairly quickly lose confidence in what can feel like an economic bubble of sorts. And by the way, that would not just be devastating for the energy sector in some ways. That's pretty much propping up the entire US economy at this point.
It is. I think it's unlikely that's going to happen. I mean, well, let me say, first of all, remember DeepSeek? People thought for a minute that was going to be that, right? It was like dramatically more energy efficient per flop. And, oh, hey, maybe this electricity load growth isn't real. And then, 2 minutes later, we were right back where we were. I can see.
I will say, sorry to interrupt. I was going to say DeepSeek was sort of a second degree related to a second variable that I think is causing all this uncertainty in AI-driven energy demand, which is not the demand for AI services or the profitability of the AI sector. It's algorithmic evolution, right? It's the fact that we might continue to invest in AI and there might be a tremendous amount of demand for AI, but AI models become much more efficient on both the training side and the inference side, such that you can consume the same amount of AI just with 10 times lower or 100 times lower energy input. And we are seeing that happen, in real time. Like AI algorithms are becoming more efficient. They have been for the past 10 years. Just a question of whether the pace of efficiency improvement changes dramatically or not. And for a moment, DeepSeek made it feel like, oh my goodness, maybe we're in a whole different paradigm when it comes to AI algorithmic efficiency.
Well, ultimately it was a Jevons paradox challenge, right? It was like hey, it's way more efficient, so we're just going to do more. And maybe there's some limit to that, but I don't know where it is. The two things you could imagine being like big new shocks to the system that kind of blow up the demand story would be on-device inference, widespread on-device inference. So it turns out, let's just imagine that actually, maybe training of new models needs to be done in these big centralized data centers, but we're going to need fewer and fewer of them as we start to asymptote in terms of their capabilities. And then meanwhile, inference moves way, way, way to the edge and becomes super compressed, and you can put your little GPU on your phone and run a model on it. And so inference actually doesn't drive the next big wave of AI data centers. That's one thing I could imagine. The second thing I could imagine in a totally different direction is that you get widespread off-grid data centers, which there's been lots of speculation and talk about the possibility of taking stuff off-grid. You don't really see it happening yet. But if I'm imagining what are major disruptions, those are the two that feel like, at scale, they could meaningfully change the picture of the supply-demand balance.
I think that's the one major supply side disruption you can see, right? Because there is, for off-grid data centers, exactly. There's not order of magnitude uncertainty in terms of how much power capacity we can build on the grid, right? Like that's something that, we can add a certain number of tens of gigawatts through the remainder of the decade, but we're not adding hundreds of gigawatts, right? Like that just is not possible. So the one way you could potentially step up by maybe an order of magnitude the amount of new data center load you serve is by bypassing the grid and developing data centers in the American Southwest, where you have plentiful land to build data centers themselves, massive solar facilities, batteries, etc., and a little bit of backup gas generation, such that you can build with the same level of reliability and confidence you have, and then get a fiber connection rather than have to build a whole lot of new transmission. It's way easier to imagine building lots of new fiber to a concentrated region of the country where you have really good solar resources than it is to imagine building, massive amounts of new interregional transmission lines for electric power.
Okay, so maybe to wrap this one up, I'll force us each into just like a yes/no here. 2030, let's pick 5 years from now. Has the supply-demand balance meaningfully shifted back in the other direction? Or are we still in this very supply-constrained market?
I bet no.
Yeah, I bet no as well. Okay, so next question is going to dovetail off of this. Let's talk about winners and losers. We'll keep this one pretty quick. You got to pick one winner from this whole AI electricity load growth thing, and you got to pick one loser. And let's try to make it not the totally obvious winners and losers. Like,
oh man, I was going to go with the boring ones. Yeah.
No, pick whoever you want. I don't know what's obvious to you, but okay, pick one winner. Who wins in this?
I mean, anybody selling basic power system equipment, right? If you're making transformers or switchgear or conductor or turbines of almost any kind or engines of almost any kind, if you're making a way of generating electricity or delivering it, you're probably doing pretty well right now, and I think will be for at least 5 years to come, as we just talked about.
Yeah,
it's a boring one, but yes, that's one category.
I mean, I was going to go even more boring and say utilities, which is just an extension of the same thing that you've been saying. So yeah, but that's the right. You want to be in a supply constrained market. You want to be on the supply side. That's kind of obvious. Well, what about a loser though?
Yeah, that's a trickier question. I mean, I think we've talked about this on the pod before, you and I, or at least you and I have talked about it in some other context, but companies that are depending on low-cost electricity for electrification.
Or electrification, by the way, or just depending on low-cost electricity, period. Like I've been thinking about, like, if you wanted to site a new aluminum smelter, which is already electrified, you're not like electrifying an industrial process that wasn't before. If you're trying to which by the way, right, like we have tariffs on aluminum now. We should be producing more aluminum in the United States. Probably the single thing, by the way, this was going to be my answer too, but I think it's like a underappreciated problem here, which is if you're a large industrial electricity load, and you want to site a new plant, you are way at the back of the queue right now. One, you're going to pay more, and two, siting is going to get really, really hard.
Yeah, I mean, electricity consumers generally, unfortunately, I think are going to be losers from this boom in demand. And it's easy to sort of like blame data centers for that. It's not the fault of any individual data center development. And there are, in fact, ways you could see how, in any given utility service territory, adding a new data center, if it's done well and you have the right contract in place with a creditworthy data center operator, and they're paying for their fair share of system upgrades and then some, that you could actually reduce costs for all the other ratepayers from a single data center. The problem is all this pressure collectively on the power system and on the supply-demand balance for every element of that system is causing prices to go up all over the place, right? So any amount of growth is more expensive than it used to be, and in addition to that, we're encountering all of this growth at a time when the core system needs upgrading and hardening and all that to boot, right?
Yeah, and I think, like, yes, the price is one problem and the siting is a second problem. And they're both challenging, but I think the siting one might actually even be worse for large loads. Just because, like, if you are trying to, if you're 100 megawatts, like that's the load that you need, and you're trying to find a site that can host 100 megawatts, there's very little chance that one of the 100 data center real estate developers has not already tried to find that site and buy it, and there's competition for it. It's just really difficult to do. And then your willingness to pay is going to be lower probably, because probably whatever you're doing is some industrial process that's lower profitability, at least conceptually profitable relative to data centers where the money is flowing freely, right? Like, so it is really challenging.
Someday theoretical profitability, exactly.
Yeah, exactly.
I mean, I will say this is where we get back to the concept of off-grid large power facilities, large loads sited off-grid, right? I mean, we have not seen it start to happen yet, but there's a strong theoretical case to be made that if you have an industrial facility in particular where you don't need to be sited in any particular location, so long as you can get, so long as there's people that can work there, so long as you are near enough to highways and rail access, other modes of transportation to bring your goods to market and people to come work at your factory, like there should be places now. I think there was a great paper late last year from Scale Microgrids and Stripe analyzing the opportunity for mostly solar-powered microgrids in the U.S. Southwest, and there's plenty of room to build those sorts of facilities. And actually, like manufacturing facilities probably lend themselves to doing that even better than data centers because they really are much less latency sensitive. I mean, so again, so long as you have a route to get your stuff to market, then it doesn't matter so much where you're sited.
Yeah, although that's becoming increasingly true of data centers as well. At least depends on the use case, but you're seeing them get cited all over the place now. Okay, let's move on to talk about a few specific technologies that have been the kind of, I'd say the darlings, or at least some of the darlings of this wave of AI power demand growth. So we're going to do one interesting question on nuclear, one on geothermal, one on GETS, grid enhancing technologies. Okay, here's the nuclear one that I think is the interesting question in front of us in nuclear, which is, let's assume there will be a nuclear renaissance in the United States. Let's just posit it's going to happen. Will it be comprised of a Cambrian explosion of a bunch of new reactor designs? A lot of these, let's call them Gen 4 reactors, SMRs, microreactors, all this kind of stuff. There are dozens of venture-backed companies which are gaining a lot of steam and momentum. The US DOE is running this reactor pilot program with 11 of them. Will we see the deployment of, 10 or more new reactor types into commercial systems? Or will this nuclear renaissance basically be comprised of AP1000s, which is the one Gen 3 plus reactor that has been deployed internationally over and over again, manufactured by Westinghouse, or maybe the one SMR reactor that seems to be furthest along, which is the GE Hitachi BWRX 300. That's the one that's going to get built in Ontario and maybe TVA territories. That'll be the first one. So the basic question is like, are we going to see a ton of new reactors deployed in the market? Or are we mostly just going to see the one or two that sort of have already gotten mostly through the gauntlet?
I think the short story is there already is a nuclear renaissance happening globally. Hasn't quite caught on yet here in North America or in most of Europe, at least Western Europe. And we can see the answer playing out, which is that there's just a few reactor designs that are getting traction. And basically, it's the ones that you mentioned, especially the AP1000 at this point. And China is very much driving that. And it's actually one area of technology in which China is still buying a significant amount of technology from a Western vendor. And I think that same pattern is going to play out in the nuclear renaissance as much as it happens anywhere in the world. There just can't be a Cambrian explosion of new reactors. The industrial logic of the nuclear industry just doesn't lend itself to that. I think best case scenario, it's bad for the industry if you end up with 4 or 5 competing reactor designs that are relevant in any given region, because really what you need for nuclear to come down the cost curve is you need economies of scale throughout the supply chain, and you need to really come down the learning curve when it comes to deployment. And I would say that learning curve extends all the way from policymakers and regulators down to people doing construction on the site. And that's only going to happen if you pick 1 or 2 designs basically per region and you just deploy the hell out of them. So maybe we'll get one Gen 4 reactor champion, one SMR champion in each region. Any more than that, I'm not sure it's really sustainable.
Yeah, I think in the long arc of history here, the gas turbines are a decent proxy here, and there is an oligopoly of gas turbine suppliers, right? Like the 3 big ones are GE, Mitsubishi, Siemens, and they control 70+% of the market. I don't really see why nuclear should be so different from that. And so if they're going to end up, and I guess you could argue maybe there are different use cases for smaller versus larger, but that's also kind of true of gas turbines as well. So I feel like, to me, I don't really see the argument why there should ultimately be many, many of them. And if there are ultimately only going to be a couple or a few, then yeah, it feels to me like you got to make the counter argument to why the ones that are furthest along can't ultimately be the ones that are furthest along, by the way, with companies that have balance sheets behind them, as opposed to all the startup reactor companies. it just feels tough, right? We have some public companies, right? Like Oklo's a public company now selling reactors. NewScale's a public company now trying to sell reactors. Like, I don't know. I don't know how it doesn't end up just being kind of a bloodbath for a bunch of those companies, and then a few of them sort of make it through at the end of the day.
Yeah, I think the next 5 to 10 years are pretty crucial for any of those more startup-y reactor companies, because there's clearly not room for more than a few of them. So they have to. This is the time to cement themselves as the maybe one or two that make it through the ringer and start to gain significant scale. And totally agree with you on the sort of comparison to the gas turbine market. You could also say there's a parallel here in the aviation market, right? Any really big, complex piece of machinery that takes tremendous amount of institutional knowledge, not to mention IP, to build, and has really high safety and regulatory concerns
Rocket
attached
engines,
to it.
Yeah, sure.
Yeah.
You heard the phrase speed to power a lot lately, but here's what it really means. AI data centers are being told that it will take years to get grid power. They can't afford to wait, so they're turning to on-site power solutions like Bloom Energy. Bloom can deliver clean, ultra-reliable, affordable power that's always on in as little as 90 days. Bloom's fuel cells offer data centers other important advantages. They adapt to volatile AI workloads, they have an ultra-low emissions profile that usually allows for faster and simpler permitting, and they're cost-effective too. That's why leaders from across the industry trust Bloom to power their data centers. Ready to power your AI future? Visit bloomenergy.com to learn more.
The grid wasn't built for what's coming next. Electricity demand is surging, from data centers to EVs, and utilities, they need reliable, affordable solutions that don't require building expensive new infrastructure. Energy Hub helps by turning everyday devices like smart thermostats, EVs, home batteries, and more into virtual power plants. These flexible energy resources respond in near real time to grid needs, balancing supply and demand. Plus, they can be deployed in under a year and at 40 to 60% lower cost than traditional infrastructure. That means more reliability, lower costs, cleaner energy. You can't get much better than that. And that is why over 120 utilities across North America trust Energy Hub to manage more than 1.8 million devices. Learn more at energyhub.com or click the link in the show notes.
All right, that's nuclear. Let's do geothermal. And we'll focus on the subclass of geothermal that's the kind of new one, which is enhanced geothermal. So enhanced geothermal has garnered a lot more attention of late, I would say, in part thanks to the fact that Chris Wright, Secretary of Energy in the US, is pretty bullish on it, amongst a bunch of others. And the standard bearer, the flag bearer of enhanced geothermal is Fervo. Fervo is currently in construction on their first commercial project. It's called Cape Station. And I think their expectation is that they hope to have 100 megawatts out of I think it's a 400 megawatt project online in 2026. So that'll be the first enhanced geothermal project ever built, commercial enhanced geothermal project ever built. And I think the interesting question to me is, if we assume success there, let's assume Fervo does bring 100 megawatts online in 2026, how big a watershed moment is that for EGS? How much does that tell us about EGS's ability to scale globally and quickly from there? Or is it closer to, and this is not going to be fair to EGS because it is not the same situation, but just to give you the other pole of a possibility, in nuclear fusion, it was like the watershed moment was when somebody reaches energy break even, Q is greater than 1, and NIF did it, but it was on a totally uneconomic reactor. So there's sort of a race to be second to do it on a reactor design that could theoretically be commercial. So it's not really the watershed moment that I think people thought it might be. So anyway, for Fervo with Cape Station, like, let's say they succeed. What does that make you think about EGS?
It's a great question, because I think I have complicated feelings about this one. I think the answer, you could frame the answer either way. In one sense, I think it is a watershed moment. It's a flag that is planted for enhanced geothermal that demonstrates that it can be done, that it can be done reasonably cost effectively. I'm sure there's a tremendous amount of learning that happened throughout the development of first the demonstration project that Fervo has built, and then onward to this full scale commercial project. And we also know that there are a number of companies that are hoping to be fast followers in the enhanced geothermal space, that believe that they too can leverage the existing oil and gas supply chain for hydraulic fracturing and horizontal drilling, and some of the same service providers that Fervo has utilized, where some of that knowledge now resides, and also develop enhanced geothermal projects. And so there's reason to believe that Fervo is the leader and Cape Station is kind of the starting gun. On the other hand, my own view is that geothermal, unfortunately, is inherently going to be a slower technology to roll out, even after that starting gun, than something like solar was. Like you could argue we're at a point. Fervo is kind of initiating a geothermal market, and that we're at a point sort of like solar was at maybe in 2008 or 2009, when the very first relatively small but still meaningful utility scale solar projects were being built. But solar, especially at that point when there was so much open land near transmission interconnection access points, it was just so easy at that point. Once the economics made a certain amount of sense and there was policy support for large scale solar to roll out extremely quickly. And geothermal, just inherently, because of the fact that there still is risk in drilling and exploration for geothermal resources, that there's a more complex supply chain that needs to be mobilized. I think that geothermal will inherently take more time. So, while Cape Station is this marquee event and it should feel like afterwards things move very quickly, I think we might be disappointed for a few years while we wait and see more projects pretty slowly move to get off the ground. So I think we're going to want it to be this inflection point kind of event, but I think that the inflection is going to be much slower and happen over the next 5 years, and that geothermal will really be positioned to take off more so in the 2030s than in the late 2020s. That's my bet at the moment.
Yeah, I think that's probably right. The big difference between solar and geothermal, obviously, solar, photovoltaic panels are a product. You can put them anywhere. There will be different ambient conditions and they'll perform differently, but you sort of know what they are and the product is the same everywhere. Geothermal, enhanced geothermal, right? There's all this subsurface risk that you have to mitigate. It's all pretty site specific. So we've done it in oil and gas, right? That's the whole concept here, is that we've found a way to scale hydraulic fracturing across lots of different geologies and lots of different regions. But there as well, it did take quite a while from the first well that was ever fracked, for example.
Yeah, and again, I would say one more interesting facet of geothermal, I think, is that its relationship, enhanced geothermal's relationship with the oil and gas industry, is also both a positive and a negative. On the positive front, you have this highly skilled engineering and technical field workforce that can very quickly, theoretically, be mobilized to support the geothermal industry. There's hundreds of thousands of people around the country that work in oil and gas today, some of whom probably have a keen interest in making a transition into providing cleaner energy and have the skills to do it. So that's the positive. On the negative side, you also have what at times can be an extremely lucrative industry who can pay those people for their skills. And so I actually think to some extent the timing and the pace of geothermal deployment might also depend on the alternative for that skilled workforce. So high oil and gas prices, really rich oil and gas market, harder to convince drillers to go to work in your geothermal field. That's riskier, takes longer to pay off, et cetera. If we have for extended period, low oil and gas prices and that market's feeling slower and less exciting, you may be able to mobilize more of the existing workforce.
All right, let's do one last one on grid enhancing technologies. So grid enhancing technologies is an umbrella term for a bunch of different things. You can describe some of your favorites within them. Here's the interesting question. Grid enhancing technologies I think anytime anybody hears about them and what they can do and what they cost for the first time, and then they hear about the current situation in the power sector, the obvious reaction to it is like, well, that's a no-brainer. Like, of course we should do that basically everywhere that we can. It's a cheap way to get more capacity flowing through the lines that we already have, avoiding the need to build new transmission, which is really, really difficult to get done. It has started to happen, but I think it has been frustratingly slow to a lot of people. Why is the question? I guess first describe your favorite technologies, and then why have they been slow to take off in a macro sense?
Yeah, I think the two that make the most sense to people, and again, seem like no-brainers on paper at times, are advanced conductor technology. So basically, electric conductors, new wires made of different materials that can carry more power using the same footprint of transmission lines. So basically more power with the same or less weight. And if you can carry more power with the same or less weight on basically the same kind of towers that you're already carrying power on today, you can theoretically reconductor an existing transmission corridor. You can swap out the old conductors for new conductors without changing the height of the towers or anything that would trigger a new permitting requirement or potentially get some of the your friendly local NIMBYs involved, and just strictly carry more energy over the same transmission corridor with basically no downside. Sounds great. The other category of gets, which I think deserves a lot of the positive attention that it receives, and is often also sounds, at least on paper, like a no-brainer, is dynamic line ratings, where today transmission lines are rated fairly conservatively for kind of the worst case or near worst case environmental conditions, oftentimes on a seasonally adjusted basis. So you have a rating in the summer and a rating in the winter, just to make sure that no matter what, at any given time, you can safely carry the amount of power over those lines that you are carrying. Dynamic line ratings allow you to monitor the lines in real time for temperature and the amount that the lines are sagging, or the amount that they're blowing back and forth in the wind, so that you can rate them dynamically in real time, and potentially in many cases carry more power over that line than your static conservative rating would allow. And so, yeah, again, the question is, why have we not seen more rapid adoption of these categories of technology in the past? Number one, I would say, is because we haven't been in the extraordinary demand growth conditions that we are today, even just 3 years ago. So there wasn't just enough of an impetus in the past, that the market is more conducive for grid enhancing technologies today. But, secondarily, I think the reason that we haven't seen gets be deployed as quickly as it sounds like they should be, there's a few reasons. One is the natural conservatism of the utility industry. And, what I mean by that is, this is an industry that is accustomed to operating particularly transmission and distribution assets with minimal intervention, human intervention, as these are big, long, remote assets deployed everywhere. You don't want to have operators there all the time. For decades and decades at a stretch, this is high voltage infrastructure that, has immediate acute human safety implications and environmental safety implications. And so adopting any new technology, like, this is the most conservative part of a relatively conservative industry. And I think for good reason. It's just very difficult. There's a lot of validation required before they're going to put something into the transmission system that is really fundamentally new in any way. And secondarily, I think because oftentimes there is a lot more complexity in deploying gets than it kind of sounds like in the initial pitch. The grid is this big, complex, integrated system, and just improving the ampacity of one stretch of transmission, for example, changes the way that the grid operates in ways that you need to, study holistically. If you're going to change that stretch of transmission line and expect to get higher throughput, you also need to upgrade the substations at both ends, for example. Sometimes that might require you to, make other upgrades on the system at the same time. And so my sense is that the adoption cycle for gets is just inherently longer than frankly, like I would have liked to have seen it be. And I am hopeful that we're in a different paradigm now because of higher demand, but still expecting that we're going to need to be patient with rollout of any of this technology.
Yeah, I think one thing we've learned in this sector is like almost never is there like a galvanizing event or moment that suddenly everything moves extraordinarily quickly and adoption of new technology occurs overnight like it does in some other sectors, to be fair. And there are good reasons why that's not true in electricity. But when something does start, a new technology does gain momentum, it usually has like a decade plus, maybe a couple of decades worth of steam that it can ride on. So the thing for me about gets is like, it feels like the momentum is building now, finally, in a way that it hasn't been historically. And if so, then the expectation shouldn't be that like you get a 10x overnight increase in gets deployments, but it should be that you are steadily deploying more and more gets for like a very long time. And that to me seems like it should be the answer. Like these are, yes, there's risk and we have to get over the risk, but assuming that everything works as we expect it should, it is an obvious set of technologies to deploy in the electric grid, period.
Yeah, until recently, a lot of gets technology has been stuck in what we occasionally call at EIP utility pilot hell, which is a bad place to get stuck. Or if not pilot hell, then really consigned to niche use cases where you have no other option, and it's obvious that gets will solve a very, very specific problem in a specific location. I think we're starting to move beyond that, but again, agree, it's not going to be probably similar to geothermal. Like there's just, for different reasons, inflection point does not mean 1 to 10. It means 1 to 2, and then 2 to 3, and then maybe 3 to 5, and gradually over the course of 10 to 20 years, you get to that 10x.
All right, Andy, we're out of time. More questions to come.
But my question for you, Shayle, did you realize that Catalyst was going to become also not just one of the top energy podcasts, but also one of the top data center and AI podcasts? Would you have made that bet to yourself a year and a half ago?
It's interesting. I'm constantly trying to self-reflect on whether I'm spending too much time on this podcast talking about this topic and like all the little nuances of it and the tentacles that it is drawing. But it is that important, I think. And it is that dynamic and it is that uncertain. And so I forgive myself.
I'm just saying the fact that you can call to mind on-device inference as easily as carbon dioxide removal is a new thing for you personally and for Catalyst.
It's true. This is what's happening in the world. So we got to figure it out. All right, Andy, we'll talk again soon.
Thanks, Shayle. See ya.
Andy Lubershane is the head of research and a partner at Energy Impact Partners with me. This show is a production of Latitude Media. You can head over to latitudemedia.com for links to today's topics. Latitude is supported by Prelude Ventures. This episode was produced by Daniel Woldorff. Mixing and theme song by Sean Marquand. Stephen Lacey is our executive editor. I'm Shayle Kann, and this is Catalyst.